Hi, my name is Mark Rouleau. I'm one of the mathematics consultants in the Learning Success Center at Mount Wachusett Community College. In this video, I will explain hypothesis testing for the mean for your statistics class. First, a review. You have to understand the differences between a population and a sample. A population will be represented by this large circle here. And let's say we're talking about fish in a lake. Now, if we measure the lengths of these fish and plot them out, we could get a distribution curve. These lengths will have a mean. The population mean of the fish will be represented by this lowercase Greek letter mu. Next, we could be talking about the standard deviation of those lengths. Again, for a population, that is represented by this lowercase Greek letter sigma. We can also talk about the population size, that's represented by capital letter N. Now, for many reasons, it can be impractical to impossible to catch every fish in this lake. So we might not really know the population mean, but we could take a sample. Sample will be represented by this smaller circle. And again, the lengths of the fish in this sample can be measured, and we can find the sample mean. A sample mean is represented by x bar. And the sample standard deviation for the lengths of the fish, that's represented by lowercase letter s. Also, the size of the sample will be represented by a lowercase n. Now, when I take a sample and find a sample mean, it could be a little bit lower than the population mean. It could be a little bit higher. It might be actually very, very close to the population mean. But remember, if someone else were to take a sample, they would probably get a different sample mean. Also, it's very important to understand what all these symbols represent, especially since we have a formula that has, for example, both x bar and mu. You'll need to know which is which to solve the problem correctly. When we conduct a hypothesis test, we are making a claim about a population parameter, possibly the population mean, but it could be a population proportion, standard deviation, or another parameter. And then we test the veracity of our claim based on the statistic we get from a sample. For example, let's say I claim that the average student at MWCC has $30 in their wallet or purse. That is a claim about a population mean. If we take a sample of MWCC students and find out that they have a sample mean of $25, you might conclude that I was wrong with my claim. However, I might still be correct. We might have just gotten an unusually low sample. But then we ask, how likely or unlikely is it to get such a low sample mean, given everything, including sample size? And then we compare that to our tolerance level, called a level of significance. If the probability of getting a sample of $25 is low, we have less confidence that our claim was correct. But if the probability of getting a sample of $25 is reasonable, then we have more confidence that the claim could be correct. This can go the other way too. If I claim the population mean is $30, and our sample mean turned out to be $30, you might have thought I was correct with my claim. But the true population mean could have been something else, $25 for example, and we could have gotten an unusually high sample mean. Unless we survey the entire population, we can never 100% know whether we were justified in our result, but we can have more confidence in our answer when we use a low level of significance. The first step in a hypothesis testing problem is to identify the claim and then to figure out the complement of that claim. A complement is kind of like an opposite, except a statement and its complement must cover all possible outcomes. The complement of mu equals 12 is mu does not equal 12. The complement of mu is less than 40 is not mu is greater than 40. It is mu is greater than or equal to 40, because we have to allow for the possibility of equality. And the complement of mu is greater than 165 is mu is less than or equal to 165. In these problems, we always test what we call the null hypothesis, also called H0, H0, or H null, and is usually written as H with a little 0 to the side as a subscript. The words null and not also mean 0. The alternative hypothesis, usually called HA, H alpha, or H alternative, and is written as H with a little a and the subscript next to it, is the complement of the null hypothesis. In some problems, the null hypothesis will be the claim. In other problems, the claim will be the alternative hypothesis. What you need to remember is that a null hypothesis must contain a condition of equality, either equals, less than or equals, or greater than or equals. Then the alternative hypothesis will be the complement of H0, either not equals, greater than, or less than. When you start these problems, identify your claim and write that down. There will be a lot of numbers thrown at you in these problems. Which one is the claim? Remember, the claim will have something to do with the population, not a sample. If the claim contains a condition of equality, call it H0. If the claim does not contain a condition of equality, write it down as H alpha. Whether your claim is H0 or H alpha, also write down the complement. H0 is going to be written on top, and H alpha is written underneath it. When we make our hypothesis test, it is always a test of the null hypothesis, and we will arrive at one of only two results. Either there is enough evidence to reject the null hypothesis, or there is not enough evidence to reject the null hypothesis. To test the null hypothesis, we will conduct either a left-tail test, a right-tail test, or a two-tailed test. How do we know which one to use? The trick here is to look at the inequality in H alpha. If the inequality is less than, then we will be looking at the lesser side of our standard normal curve, that is, a left-tail test. If the inequality is greater than, then we are looking at the greater side, which indicates a right-tail test. If the inequality is not equal to, then we are going to conduct a two-tailed test. In these problems, you will also be given a number, abbreviated alpha, called the level of significance. Note, this alpha is unrelated to the alpha in H alpha. The level of significance indicates our level of tolerance to the possibility of an unlikely sample. Let's look at an example. Let's say a researcher claims that the mean amount of tuna fish eaten per year in a population is no more than 8 pounds, and that the population standard deviation is 1.2 pounds. Next, a sample of 40 people is taken, and their mean tuna consumption is 8.5 pounds. Is the claim justified? Let's use a level of significance of 8%. First, make sure you can identify the claim. The problem states that the mean in the population is no more than 8 pounds. You must be careful with the wording of the claims. No more than has to be interpreted as less than or equal to. And since the claim has a condition of equality, it becomes the H naught in this problem. Our H alpha is the complement. Mu is greater than 8 pounds. Therefore, this will be a right tail test. There are two ways to test your null hypothesis. The first way to do the hypothesis test is to identify a critical value or critical values based on the level of significance to determine your rejection area or areas, and then see if our sample falls in the rejection area or not. This example is a one-tailed test, so there will be one rejection area. The rejection area in this right-tailed test is to the right of the critical value, and that area is equal to the level of significance, 8%. Use your z-table to find the z-score that gets us 8% to the right, which is also an area of 92% to the left. I come up with 1.41. Next, I find the z-score of my test statistic, which is based on the sample. If, as in this example, I am testing for the mean, the formula for my test statistic is z equals x bar minus mu over sigma divided by the square root of n. This looks like the formula we've been using to find the z-score of a single person or object, which is really the same as the previous formula when n, the sample size, equals 1. If you're using your calculator for these problems, please use parentheses for your numerator and denominator. Otherwise, you could end up with an order of operations issue. In this example, the value of the test statistic is 2.64. We compare the value of the test statistic with the critical value and see if the test statistic falls in the rejection area or not. If it does, as it does in this case, then there is enough evidence to reject the null hypothesis. The other way to check your null hypothesis is to compare the p-value from your test statistic with your alpha, which is your level of significance. The p-value is based on the area in the tail of your test statistic. If you have a one-tailed test, the p-value equals the area in the tail of that test statistic. But if you are doing a two-tailed test, the p-value equals the area in the tail times 2. I'll explain this better in a moment. Then, compare the p-value with alpha. If the p-value is greater than alpha, then you fail to reject. If the p-value is less than or equal to alpha, then you will reject H naught. In this case, we find the area in the tail of the test statistic of 2.64. This is a right tail, so we use the z-table and get the area to the left of 2.64 and subtract that from 1 to get the area to the right of 0.0041. This is our p-value, since it is a one-tailed test. Compare this to alpha, which was 8% or 0.08. Since the p-value is less than alpha, there is enough evidence to reject H0. Why does this work? If we have a one-tailed test, then the rejection area in the tail is just alpha. If the p-value is smaller than alpha, then it fits completely inside the rejection area, and therefore we must reject H0. If the p-value is greater than alpha, then the z-score of the test statistic falls outside where the critical value is, and we then, again, would fail to reject H0. What's so different about a two-tailed test? In a two-tailed test, our alpha is split in half. Let's say alpha equals 0.10. So half of the rejection area, 0.05, is in the right tail, and half, 0.05, is in the left tail. If I calculate my test statistic and get an area in the tail of 0.07, it is clearly outside the rejection area in this tail. But alpha in the two-tailed test is the sum of the areas in both tails. 0.07 is smaller than 0.10, but we wouldn't reject in this case. To account for the two-tailed test, we must take the area in the tail of our test statistic and multiply it by 2, which in this case is 0.14. This is how we get the p-value for a two-tailed test, and it is this number we compare with our level of significance, and in this case, we would fail to reject H0. Once you have rejected H0 or failed to reject H0, you may be asked how this relates back to your original claim. Remember, a claim will be H0 in some problems and H alpha in other problems. And since we have two possible results from the hypothesis test, reject H0 or fail to reject H0, there are four possible outcomes for your claim. Each of these outcomes is dependent, again, on that level of significance. If your claim was H0 and you reject H0, you would say there is enough evidence to reject your claim. If your claim was H0 and you fail to reject H0, you would have to say that there is not enough evidence to reject your claim. Note, not rejecting a claim is not the same as supporting a claim. Remember, we can only reject H0 or fail to reject H0. It's like a jury trial. The foreman never reads a verdict finding a defendant innocent. It's either guilty or not guilty. If your claim is H alpha and you reject H0, you can now say there is enough evidence to support your claim. A good experimenter will put their claim as H alpha to give the claim a chance to be supported, which sounds better than, well, we couldn't reject it. Finally, if your claim is H alpha and you fail to reject H0, you must say there is not enough evidence to support your claim. And remember, you can never be 100% sure of your outcome unless you survey the whole population, which is usually impossible or impractical to do. There's always a chance to make an error. If H0 is really true, but your sample is unusual, you end up rejecting H0. This is called a type 1 error. This would be equivalent to an innocent man being convicted of a crime. If H0 is really false, and H0 is not rejected, this is called a type 2 error. This would be the same as a crooked defendant being found not guilty in court. Let's try another example. A car dealership advertises that the mean time for an oil change is less than 15 minutes. The population standard deviation is 0.7 minutes. A sample of 30 oil changes revealed a mean time of 14.8 minutes. If the level of significance is 0.05, do we reject H0? And what can we say about the claim? First, I'll write my claim. Mu is less than 15 minutes. Since there is no condition of equality, this must be H alpha. I'll then write the complement above, which is H0. Mu is greater than or equal to 15. Let's try method 1 to solve this one. That is, I find the critical value for this left-tailed test. We know it is a left-tailed test because the inequality in H alpha is the less than sign. And 0.05 is to the left of that critical value. Using the z-table, I get a z-score of negative 1.645. Now, find the value of the test statistic. H bar minus mu over sigma divided by the square root of n. And I get a value of negative 1.565. This does not fall in our rejection area, so at this level of significance, there is not enough evidence to reject H0. At this level of significance, we cannot reject H0, but the claim this time was H alpha, so we would say there is not enough evidence to support this claim at the 5% level of significance. Now, on the other hand, if the level of significance was different, 10% for example, then we would get a critical value of negative 1.28. And at this level of significance, we would be able to reject H0, and there would be enough evidence to support the claim. So that level of significance can be pretty important. Let's try another example. A company CEO claims that the mean temperature of the coffees in their chain is 195 degrees. The population is normally distributed and has a standard deviation of 4 degrees. A sample of 25 coffees shows a mean temperature of 193 degrees. Is there enough evidence to reject the claim when alpha equals 0.01? Let's use method 2 and use a p-value to solve. Once again, the first thing I'm going to do is I'm going to write down my claim. The claim says that mu equals 195. This has a condition of equality, and therefore it is our H0. And then I will write down the complement. Mu is not equal to 195 degrees. To get the p-value, I first calculate my test statistic, x bar minus mu over sigma divided by the square root of n, and I get a z-score of negative 2.50. This has an area in the tail of 0.0062. That comes from the z-table. And as this is a two-tailed test, we multiply this number by 2 to get a p-value of 0.0124. Since the p-value is greater than alpha, we fail to reject H0. The claim was H0, and since we cannot reject H0, we would say at the 1% level of significance, there is not enough evidence to reject the claim. The procedures we've followed to this point were for situations when sigma was known and either the population was normally distributed or n is greater than or equal to 30. If sigma is unknown and either the population is normally distributed or n is greater than or equal to 30, then we can conduct a hypothesis test using a t-test. In a t-test, we use a t-table. There's a t-table at the back of your book, or you can find them online. As we are only testing one variable, we say that we have n minus 1 degrees of freedom. To use a t-table, find your number of degrees of freedom down the first column of the t-table, Then find the column with the level of significance, alpha, and whether it's a one-tail or a two-tail test, to get your critical values. Remember, if it is a left-tail test, your critical value will equal the negative of the number from the t-table. And in a two-tail test, your critical values are the positive and negative values of the number from the table. Everything else is more or less the same as the previous examples, except the formula for the test statistic for the mean is t equals x bar minus mu divided by s divided by the square root of n, where s again is the sample standard deviation. Let's try an example. A used car salesman says the mean price of his cars is less than $20,000. A random sample of 14 cars shows a mean price of $19,500 and a sample standard deviation of $1,200. Is there enough evidence to support his claim with an alpha of 0.05? Assume the population is normally distributed. First, we'll write down the claim, which is mu is less than $20,000. The claim does not contain a condition of equality, so it is H alpha. The complement, H naught, says that mu is greater than or equal to $20,000. Because sigma is unknown and the population is normally distributed, we will use a t-test. From the t-table, we use 14 minus 1, or 13 degrees of freedom, with a one-tail test and an alpha of 0.05, which gets us a critical value of negative 1.771. We will reject H naught if our test statistic is lower than this critical value. Now, get the value of the test statistic, t equals x bar minus mu over s divided by the square root of n, which gets us a t-score of negative 1.56. This is not in the rejection area, so we cannot reject H naught, and at the 5% level of significance, we would say there is not enough evidence to support the claim that the mean price of his cars is less than $20,000. The problems we have been working on have covered hypothesis testing for the mean. You may be asked to conduct hypothesis testing for population proportions, or for population variance, or standard deviation. Look for help on those topics in another video. Let us know if there was anything in this video that could be made more clear for a future update, and let us know if there are other videos you would like to see in this series. As always, check out our website for more information about services available in our Learning Success Center, or call, email, or stop by. Good luck, and I hope to see you this semester in the Learning Success Center.